First speaker, Professor Tim Sluckin, who will talk to us about fluids with an attitude, journey through the history of liquid crystals.
Okay, so those who know me will know that as a theorist I am remarkably poor at practical things, and you will see that I have two pieces of equipment here, and something is bound to go wrong. And is the technician still in the house somewhere? Because and if the technician is there at the back, and if the technician fails to help, then I know that I have two distinguished experimentalists on the front row here who can help. Okay, so for those of you that have been speaking English a long time, you'll know what with attitude means, and for those of you who are newer to English, then it's too hard for me to explain. Okay, so my very first statement is wrong, of course. It assumes that you know already about liquid crystals, and so I went to a lot of trouble to remove the jokes from this talk and to make it, if you like, more advanced and less elementary, only to discover that there were some mathematicians in the audience who knew nothing very much about liquid crystals. So for those of you that don't know very much about liquid crystals, there will be a very short introduction, and there will be much more, of course, sophisticated that comes later on. I'm going to try and concentrate on conceptual rather than... There won't be anything about devices, the version of this talk that I often give, because most people are interested in liquid crystals, of course, because of their device implications. But here I'm going to be concentrating on conceptual and scientific aspects. There will be those of you that know part of this story and don't agree with it. Please wait till the end to heckle. Okay. There is, of course, when it comes to history, no universal truth. Okay. So just a brief summary for those of you who are new and for those of you who want to argue at the end. Liquid crystals are structurally intermediate between liquids and crystals. They are absolutely not crystals. There are a rich panoply of what we have come to call mesomorphic phases in between types. They bear a non-Newtonian hydrodynamics. If you're a statistical mechanician, you talk about broken symmetry, which means that one direction becomes special. There are topological defects for which the correct way of studying it is, of course, a mathematical topology. It depends on the phase. And they are optically birefringent, which is why they are so useful in devices. Here's a little picture. Right on the left-hand side, you will see what is known as the nematic phase. And you can see that the molecules are made out of rods. They might be made out of disks, but at any rate, and they're all pointing in roughly the same direction. And on the right-hand side, you will have seen that the directions, that there are now layers of molecules. And that's the smectic phase, the smectic A phase, because the molecules are directed perpendicularly to the layers. Right here on the right-hand side, you'll see another smectic phase in which the molecules are still in layers, but now roughly speaking, at some kind of angle to the layers. And on the left-hand side, you will see what's known sometimes known as the cholesteric. Now it's politically correct to call it the chiral nematic phase. It's chiral in the sense that here are all sorts of molecules lining up, but they twist around. You can see that each layer has a slightly different twist, and there's a length over which the twist is repeated. So it's a helical configuration. The repeat length is known as the pitch. Right. Those of you that know about liquid crystals, of course, will know about these things already. And here is a sketch of the kind of phase diagrams that we see. Right. At the top is the, let me find this. There are the disordered phase, the molecules pointing in any old direction. Down here are crystals. Crystals are K because the first people to look at this kind of thing were Germans, and in German, crystal begins with a K. Actually, in the original German that people did to discuss this, the crystal also had a Y, but it now has an I for various different spelling reasons. Okay, so as we go down in this picture, the temperature is decreasing, and gradually the system is going between the normal liquid, which is the isotropic equal directions, to the crystalline phase, in which each atom has one molecule has a nice position, and as you go in this direction, in some sense, you are turning on things that we generally regard as having something to do with crystallinity. But if you want to argue with things with exactly what we mean by things that we generally regard, that will be another several hours. Okay, here's a sort of overview of the history before we discuss various details. Right, this is a late 19th century phenomenon. The liquid crystals were first observed by Reinitzer and Lehmann. I will come back to them in a moment. The first time it was synthesized, which was in 1890. We had to wait until 1922 before we had a reasonable idea of what was actually going on inside, as opposed to, gosh, aren't these things peculiar, right? The thing that is missed out there is the first patent didn't occur until the mid-1930s. That was in this country, when this country was still a great industrial power, and but they were trying to make TVs. Well, actually, the materials they were using would have blown up, but that's a separate question. Whoops, see, I pressed the wrong button. Okay, actually the first time that these things were, the patent that actually got used is 1971. So when somebody says to you, why are you doing this? Is this relevant for our lives? The answer is, listen, you've got to wait. You really do have to be patient in science and engineering. Okay, so it's in the 50s that we have various different kinds of theories, molecular field theory in 1960s, Ericsson, Leslie, hydrodynamics, and by the time we get to the 1970s, there are colleagues here, if I look for them somewhere, who remember some of this already. And of course, the first LCD TVs, 1988. A parallel sort of current, intellectual current, is that of colloids, and of course, nowadays there is particular interest in combining ideas from liquid crystals and from colloids. They date from the 1860s, and again, there's a Thomas Graham house here in Cambridge, and colloids are droplets of something in something else, and at least sometimes there is competition between the colloidal technologies in your Kindle, for example, and the good liquid crystal technologies, for example, in your iPad. Okay, and a general point is that colloids and liquid crystals are the first exceptions to the old-fashioned solid-liquid gas classification, which in some sense goes back to ancient Greek times, and in a more sort of profound way, it's also the beginning of the end for philosophical dualism, the idea that living things and non-living things are fundamentally different, and that you require a god to do some breathing into pieces of clay and they will come alive. And liquid crystals are arguably the point at which we can start to think about how physiology might be based on chemistry. The first experiment was done by this fellow, Friedrich Reinitzer. He was working in Prague, which in those days, of course, was part of Austria, and he was actually interested in carrots for reasons that are slightly unclear, and he discovered completely accidentally that cholesterol benzoate, which is this, there are some real chemists here, but I think this is cholesterol benzoate, and what he discovered was that he had a system that melted twice, first of all from a crystal to a cloudy fluid, and subsequently from a cloudy fluid to a clear liquid. And when they melted, there were some peculiar colors, he wasn't sure, and he sent them off to a colleague who was a physicist, a crystallographer called Lehmann, and Lehmann looked at them under his microscope and had observed crystallites. Okay, so, whoops, there we are. Okay, this is me doing an experiment. And you can see, of course, these are not the same materials, but you can see, this is the kind of material now at normal temperature. This is my Bunsen burner. and here are the peculiar colors. And you can see here it is a clear liquid, the clear isotropic liquid. There is the cloudy liquid crystalline fluid. And the question, of course, you wouldn't have looked at the cloudy fluid and said it's liquid crystalline. Okay, so this fellow, Otto Lehmann, is the real pioneer of liquid crystal work. It took some time for things to clarify, as it were. He found various different kinds of materials which he called fließende Kristalle, schleimig flüssige Kristalle. So there were various crystalline Flüssigkeit, crystalline fluids, various different kinds of Tropfbar, things that can make drops. Okay, here, right. He was a crystallographer, which of course in those days was regarded as looking at crystals. Not, of course, in those days there were no X-ray crystallographers yet. So he had a polarizing microscope with a heating stage, and he used it to apply to Reinitzer's cholesterol benzoate, and eventually he identified birefringence, right, which was at that stage a property only of crystals, and flow, which was a property of liquids. And he said, okay, if you put them together, obviously you must have a liquid crystal. And so took some time. Here's a picture of his microscope. Sitting on there is the hot stage. Okay. So he's the premier pioneer. I don't want to say terribly much about him, but he was really a very powerful personality. And later on in life, he was nominated for the Nobel Prize, but was unsuccessful, much to his disappointment. And he really was the embodiment of a 19th century intellectual. He wrote, for instance, when he was rector of the University of Karlsruhe at the beginning of the 20th century, there's a wonderful essay on physics and politics, which I think many of us would be proud to have written. I just want to show you this is his very first paper on liquid crystals. And for those that are German speakers, I just want to look at this enormously long sentence, which actually has 100 words. I think if this was in Word says that if you have 20 words in your sentence, then it's already too long. And I think probably Word would crash if it had to face it. Right. So this is the Zeitschrift für Physikalische Chemie. This is what it is this is my translation, I have to say, in English. And it took a long time, and I had to divide it into 5 sentences. But even so, flowing crystals, is that not a contradiction in terms? Our image of a crystal is that of a rigid, well-ordered system of molecules. And incidentally, at that stage, the lattice theory of solids was not yet well established, right? And that was one of the reasons for big arguments. I mean, he was sure, many 19th century physicists were sure that crystals must be like that. But in those days, what a crystal was something what had facets, and you could see light shining off the surfaces. Okay. So are we not accustomed to explain flow in terms of a thermal state which induces molecular rotations and translations, and which permits molecules constantly to pass each other to and fro? There are sentences that are longer than 100 words, and it was lucky that we had a German colleague working with us. Here are some pictures of things that he saw under his microscope. These are droplets of the material in other materials. Now, in those days, there was no color photography, and actually what happened was that he had an assistant. So they took the picture, and then he had an assistant, and the assistant colored it in. So to give colors that look like the colors. But what is interesting is that they saw patterns which deformed very quickly. They didn't understand the patterns. They saw things that looked like lines of force. Look at these. And in other pictures, they saw things that they thought of that looked stain-like, right? They called them Schliere. And for those of you who do these things regularly, of course, the Schlieren texture is something with which we are all familiar. And although most things in liquid crystals are called after a person, there was no Mr. Schlieren. Okay, here's a picture of, it looks like a music hall advertisement, actually, doesn't it? For somebody giving a show at a music hall. But this is from Merck, the chemists, the same Merck, the chemists in Darmstadt, you see, who are making liquid crystals to this day, and whom we visited in the course of the preparation of our historical work. And actually, they were not, of course, expecting to make zillions out of devices at that stage. All they wanted to do was to make a relationship with, you know, a coming man, and Lehmann developed a close relationship. He needed his materials. They thought, look, these are good guys. You never know when this might be useful. And actually, of course, they more thought that this might be related to dyes. They saw all the colors. There must be a pigment in there, obviously. And so if there's a pigment in there, we can use it on somebody's, you know, Professor Warner here is wearing a grey sweater, and we obviously want it colored, don't we? And nowadays we probably know how to make liquid crystals, use liquid crystals to make his sweater colored. All right, so it wasn't in 1890, only a year after Lehmann had started to work these things, 2 years after Reinitz had made his observation, the synthetic chemist Ludwig Gattermann accidentally synthesized a liquid crystal, didn't know exactly what he was doing, but eventually synthesized something that had this double melting property, and this para-azoxyanazole, PA, it became the experimental liquid crystal of choice. Gattermann later became a famous organic chemist, but he doesn't do anything for us. Here are some pictures. Of course, these are not the original textures found by these guys, but there's some textures from my close colleague David Dunmer, who worked with me on all of this. But I haven't actually been able to discover where the word texture arrives from, but the important point is that it described these beautiful colored patterns which you observe between what they call crossed nickels and which we call crossed polarizers, and which they gave various different names. This one here was called the thread texture. It's the Schlieren texture, right? Each texture was associated with a phase, and the flow properties and the patterns seemed to be related to each other. Okay, so of course there was a question of what was going on. Nobody was quite sure. There were 2 or 3 melting points. There were cloudy, and right, the phases, it wasn't clear whether the primary property was that they were cloudy and the fact that they were birefringent was a secondary thing, or whether the fact that they were birefringent was primary and the fact that they were cloudy came out of that. I'll show a picture of that in a moment. They had but one thing that was clear was that there were structural and flow properties that were something between a solid and a liquid, and there were all sorts of ideas, and all the elderly people of our kind of age said this guy, at this stage Lehmann was in his early 30s. He was he had just got his first job, and the general view among the elderly people like Claudio and myself was that the guy was a nutter, and I've got various letters to the effect that he was in which one senior professor was writing to another senior professor to the effect that he doesn't know what a crystal is. But anyway, so some people said that it was melting twice, but obviously it was impure. And others said, no, maybe the crystals are sitting inside the liquid, and you're seeing a crystal transition, and then the crystal melts to a liquid, and then the other liquid melts. And some people said it was an emulsion of two liquids. And Schenk and Lehmann, and you can see that some of these guys were actually, some of these guys were really quite distinguished. Wolf was very distinguished. Taman, whom we'll come across, was the founder of modern metallurgy, and Nernst, of course, is also very distinguished. So, so Schenk and Lehmann said, no, it's a liquid crystal. Of course, these other guys said, well, that's all very well, but what exactly is a liquid crystal? Here's Taman, and Taman was writing at the beginning of the 20th century very polemical articles to the effect that this was all nonsense. And basically, Taman's point was that the lattice theory of solids must be right. And if the lattice theory of solids must be right, it's clearly impossible to make flowing materials and solids to be consistent with each other. Actually, just to show, über die sogenannten flüssigen Kristalle, on the so-called liquid crystals, and it's as ironic in German as it is in English. Right. This was the fellow who actually was doing, he was a kind of acolyte of Lehmann's. Later, I should say, became a Nazi, so you have to be a little bit careful in ascribing good guyness and bad guyness in all of these things. But there was a big meeting of the German Physical Chemistry Society in Karlsruhe in 1905, at which there was a big debate. And at the end of the debate, the conclusion was, well, the liquid crystals, they can't be mixtures. Whatever it wasn't because they were mixtures. They did all sorts of tricks to try and separate out the mixtures. They put electric currents, there was electrophoresis. Usually they would separate under 10 volts or 20 volts, and somebody put 70,000 volts, and still nothing happened. Right? Anyway, so there was no miscibility gap at the clearing point, and it must have been, if the thermodynamics would say that there must be a miscibility gap at clearing if it was a mixture. To begin with, there had been, and then there was an exchange. Actually, they were very gentlemanly because Taman gave his materials to Schenk to have a look at, and Schenk said, well, I've had a look at your materials. And then there was a big argument as to whose materials were purer, and Lehmann was deeply offended that his materials said that you are saying I'm a useless experimentalist. But anyway, at the end of the day, the mixtures couldn't explain the birefringence, and the surface tension obeyed what we would call a law of corresponding states. Okay, so here's some other stuff that Lehmann did. Lehmann was really, he saw his liquid crystals under the microscope, and he said, well, they are giving the appearance of looking somewhat lifelike. And he went back in the literature, and indeed he discovered, way back in 1854, Virchow is one of the most famous physiologists of the 19th century, and they discovered various results that were in the physiological literature showing that you could find materials, myelin, which occurs in nerves, which were birefringent, and he actually published a monograph entitled Liquid Crystals and Theories of Life, and he gave a talk to a joint meeting of I think it was the German Medical Society and the German Physical Society. And much later, actually in 1936, Borden, Piri, Bernal, and van Kuchen made solutions of tobacco mosaic virus and showed that they would come out as liquid crystals. And here are two pictures that date from from Lehmann's papers in 1906, showing separation of various liquid crystal-like things, and Zypher soap, you see, was a liquid crystalline material. Okay, so at this point, the chemists got in on the act, and actually the person who first sort of regularly synthesized liquid crystals was this fellow Daniel Vorlander. I'm sorry about the quality of the picture. Every time I copy it, it seems the quality gets worse, and he looks a little bit kind of suspicious, and certainly not the kind of guy that we would want to hire on our faculty. Anyway, but the most important point was, actually there's an earlier paper in which two of his graduate students published this, and which he didn't put his name on, and obviously he didn't put his name on because it was unknown that a big German professor would not put his name on a paper by two of his graduate students. So he obviously thought this is complete nonsense. But later on, about 1906, he began to look at the various different, and these meta-azoxyanazole, ortho-azoxyanazole do not exhibit double melting, but para-azoxyanazole does. These are different chemical structures, structures in the sense of the same chemical formula, but different ways of putting these things together. And incidentally, that's also an interesting point. The chemists knew at this stage what the shape of the molecules were, despite the fact that nobody had ever done any kind of scattering experiment at that stage to say, look, we can actually see it. It actually took, but there was enough sort of circumstantial evidence to say them, and everybody, of course, all the serious chemists believed that the molecules were really there and they really had various shapes. Okay, so here are some caricatured molecules, right? The cyanobiphenyl on the left. These are the the great British invention by George Gray in 1972. Para-azoxyanazole is the one in the middle, that's Gattermann's, and on the right-hand side, there's my favorite liquid crystalline molecule, the spherocylinder, used by, of course, all sensible. Everybody knows that real liquid crystal molecules look like this, none of this crap. Okay. Actually, here's an experimentalist, and I just thought this would be interesting for you to see, because this was later on in his career, as he was already getting to be, an eminence grise in all of this. And somebody said, right, I have been asked if the liquid crystalline liquid. He always calls them crystalline liquids, right? Everybody else was calling liquid crystals and stuff, but he insisted on calling them crystalline liquids. But anyway, could they be technically exploited? I do not see any such possibility. So you see, you can be really committed to experiment and so on and so forth. And no doubt a lot of his money was coming from the dye industry and so on, but nevertheless, he couldn't see any application at all. Okay, let's go back a bit. Of course, theoretical physicists tried to get in on the act. The first time that this was done was by a fellow called Emil Bohrer from what was in those days, of course, a German university, the University of Danzig. Is there a Pole in the house? Oh, all right, sorry, nothing. It was in the past, what could I do? Right, okay. Yes, it was a modified van der Waals theory. He called it the swarm theory. There was no explicit order parameter. He was looking for a theory that was analogous to the Weiss theory of ferromagnetism, which had come out in 1905, which was just, really, really new and avant-garde. But he hadn't quite managed to sort of learn how to do this properly, and his mathematical and physical pictures were not well integrated. And actually then he got sidetracked, and unfortunately he died at the age of 37. But the swarm theory turned out to be wrong, but it lasted in a number of guises until the late 1950s. And a prominent supporter was Leonard Ornstein, Ornstein-Zernike and that kind of stuff. And also, of course, the Ornstein-Uhlenbeck process, so very important if you want to make zillions on the stock market, or alternatively, I guess nowadays it's lose zillions. Anyway, right, here's another attempt from Max Born, and again, it was in 1916, and actually what he did, right, he had understood the Weiss theory better, and he said, okay, it's obvious we can carry the whole thing across. Exactly. So the paper is long, but still, actually, there's a one-to-one mapping between this and Curie-Weiss theory, but there's only one thing wrong with it. It's great mathematically. The previous guy's theory is a bit dodgy mathematically, but this one is fine mathematically. It's unfortunately that Civesi came along in 1925 and said that the liquid crystal can occur even when the molecules possess no dipole. So it failed an experimental test, I know, but it is important to state, even in this house, that if a theory fails an experimental test, Dirac notwithstanding, and no matter how beautiful it is, it's wrong. And so he decided to concentrate on less challenging problems. In 1909, Lehmann visited Paris and Geneva, gave some talks I think it was in the Collège de France. Anyway, those were really very big talks, widely publicized. Lots of ordinary people came, And anyway, there were two competing French groups, one of which was the group of Valéran, and Charles Mauguin, of whom we'll come back to in a minute, was his assistant. That was at the École Normale Supérieure. And the other was Georges Friedel and his assistant François Grandjean at the École des Mines at Saint-Étienne. Now, I think Friedel was present at this lecture, but anyway, both groups started to work on liquid crystals. Here is a picture of some of the stuff that Mauguin was doing, and of course Mauguin observed the wave guiding of the polarization, and so which is why, of course, various people at a much later stage had trouble with patents for the twisted pneumatic device. But I mean, here he was looking at fringes and stuff, so to try and see how thick the various things was, what was happening, to try and observe the transmission of the ordinary and the extraordinary way through a birefringent medium, right? And he was using Gattermann's material, the PAA, and also another one, para-azoxyphenitol, which was also developed by Gattermann. Okay, the classic, however, is Georges Friedel, and he wrote a very long monograph. Actually, it was his DSc thesis, because the École des Mines was in the French civil service, and so when he wanted to work in the university, after the First World War, the Germans reconquered Alsace, and Friedel came from Alsace, so obviously he was the right man to be professor in Strasbourg, but he didn't have the proper degree qualification, like the habilitation, and so he needed to write a test d'état, as they called them in French, and so this was his attempt to write the habilitation thesis, and it's the most cited article on liquid crystals. It's still being cited to this day. They had already published some papers before the First World War. He talks about stars as well as phases. I'm not sure that we would really, when you start talking about liquid crystals, the point at which something is a new phase and the point at which it's simply a different configuration of the same phase, it sort of becomes a slightly muddy concept. And I think that that's what he was grasping at. Right here, you can see the liquid crystals in a droplet. And you can see this is a characteristic picture that you would have seen under convergent light. And these things he called liquide à noyau. And these things are the Schlieren textures, the liquide à fils. You can see these things. Here's one where that you have 4 brushes, and somewhere else where we have 2 brushes. Actually, I've just magnified this. This is what you actually see on a larger scale. I have taken this not from a paper of Friedel, but from a paper of Lehmann, and you can see lots of little droplets, and that's why it would have been looking cloudy, actually, because you would have had lots of these little droplets scattering. Okay, so he introduced the modern terminology, that of smectic, pneumatic, and cholesteric. They're taken from Latin, from Greek, of course. Smectic comes from the Greek word for soap, and pneumatic comes from the Greek word for thread. And if you are a pedant, they have in ancient Greek adjectival endings. And I've had terrible arguments with the sub-editors at Physical Review who have told me that they are adjectives. And I have said, well, they are used as nouns nowadays, honestly. But actually, usually when they say, can you show me chapter and verse, I usually show them my books, and I say, so it's self-referential, but I'm hoping to sort of, fool them. Sometimes it works. Friedel didn't like the term liquid crystal for obvious reasons. He wanted to replace it by mesomorphic phase, right? So, right, the mesomorphic states of matter, right? His important point was that he realized that structure, rather than degree of fluidity, was the important thing. There was, of course, a correlation between structure and degrees of fluidity, but it was the molecular structure, the way in which the molecules that were organized, which was the key thing. And of course, by that time, equilibrium statistical mechanics was better established, so it was easier in the 1920s, implicitly rather than explicitly. I haven't discovered in any of his papers a mention of a Boltzmann distribution or anything, but implicitly rather than explicitly, it was easier to distinguish what might be thought of as an equilibrium phenomenon from what might be thought of as a dynamic phenomenon. So he described qualitatively the main structural features of each phase. He explained the origin of the optical signatures. And I should say it was not only a great scientific work, but a great piece of literature. And Friedel was known for his strong opinions and his acerbic style. This is my translation, but I think it gives a little bit of the flavor, right? Lehmann had the great merit of drawing attention to these substances, but he erred seriously in naming them wrongly. The terminology is inapt, despite having been ceaselessly repeated over the last 30 years. Now, they might be crystals, but it is entirely otherwise, and indeed something infinitely more interesting than would be the case if we were considering simple crystals exhibiting some unexpected degree of fluidity. And I think it's a sentiment, the last bit at least, is a sentiment with which we would all agree. Okay, here's a theory, actually, from 1917. Grandjean is very well known in the liquid crystal literature, of course. Grandjean textures, steps, terraces, lines, and planes, and so on and so forth. This theory, which appeared in the, Compte Rendu, isn't quite in the modern language, but anyway, it turns out that it was the analog of the Curie-Weiss theory of magnetism. But it was published in French. Nobody read it. It didn't enter the literature. I'm going to come back to it a little bit later on. This is the Fredericks effect. Actually, here I've spelt Fredericks as he's usually spelt in the Western literature, how he spelt his own name when he published in the West, just to emphasize that usually what happens is we put on an electric field, or rather we put on a voltage, and to begin with, we've got some boundary conditions, usually produced by rubbing the material with some kind of sandpaper, really sophisticated kind of stuff. And to begin with, the molecules point in one direction, and then when the voltage gets high enough, about a volt or so, depending on the material, it begins to turn around. But it has to be high enough, right? So there's a threshold effect. And so the boundaries are aligning the molecules, the electric fields are trying to align them, but there's a threshold effect. Without the boundary, obviously, the liquid crystals would do what the electric field was trying to tell them to do. It's an induced polarization effect for those that are not familiar with this. Whoops, there we are. Okay, this is the fellow. His Fredericks, now I've transliterated from the Russian. He created the first liquid crystal group in Russia. He was really a member of the nomenclatura. He had married the sister of the composer Shostakovich. He was deported by Stalin and died, depending on which stories you read, either in the Gulag or on his way home. But here's the beginnings of his paper. I should say, I got these papers from the Kiev library, and actually we had to work quite hard because, of course, because he was an unperson, they had been made to disappear during Stalin's time, and they had to be made to be undisappear, and somebody had obviously colored them all over in black. But here is the important picture, and that is that actually his experiments were not done in the kind of usual cell. They were actually done between a lens and a surface, and he kept they were done with a magnetic field, and this is what happened without the magnetic field. This is what happened with the magnetic field, and the point was that there was a point at which, right, something started to happen. So what Fredericks is doing is looking at a system whose thickness is changing rather than a system whose in which the field is changing. All right, it turns out to be effectively the same thing. And of course, it turns out that most modern devices use some elaboration of the Fredericks effect. This is the premier theorist of the 1920s and 1930s, Carl Wilhelm Ozane, right, known, of course, in other areas particularly of continuum mechanics. He was the director of the Nobel Institute towards the end of his life. I just want to show you some, I mean, a lot of the continuum mechanics is based on his work. This is his first, actually this is his third paper, but the one in which the now current elastic theory was developed. And it goes on, and the work is not so much looked at nowadays. And if you look at this kind of rather heavy algebra, right, tends to use, right, you see, you go on and on and on for 40 pages, but at the end of the day, it says the number of independent constants is therefore 4, right? The K11, the K22, the K33, and then the constant that we use in the cholesterics to induce the twist. Okay, this is an English version of the same thing. This L he called the direction of the molecules. You see the orientation of the axis of the molecules. So he wasn't thinking very much about statistical mechanics in those days, and the word director didn't yet exist. Right, okay. So it's interesting because he wrote in German until the Nazis came to power, and thereafter in French. The paper which is cited is his 1933 paper, but that's cited mainly because it was in English. Right, and as I said, it's difficult to follow. But I haven't gone through them all, but one of the interesting things that he is interested in is tactoid shapes. In other words, how does the surface tension compete with the elasticity? Okay, so one of the most important things was the prediction that the critical Friedrichs voltage would be independent of cell thickness. That's actually a prediction of this fellow Socha, who is a very interesting guy, but don't have time to talk about today. But he was, in some sense, Ozane's attack dog, and he was using this to argue against Ornstein's theory. And as I said, nowadays the theory is known as the Frank-Ozane-Socha theory. And here are some pictures drawn by Charles Frank in 1958, which show the various kinds of defects that one can get in liquid crystals, but not being quite aware yet of the fact that some of these were actually equivalent to each other and that you could twist them out of the way. Right, this is the beginning of the kind of maturity of the subject. Here is this is what you might call a virtual conference. Pepe Ewald, who was, of course, a premier crystallographer, got people to write articles, and so this appeared in a journal. It was a kind of conference that never occurred. And here was the conference that did occur. The British decided to get in on the act and invite the people who are in here. And you'll see that the order of speakers in this is slightly different from the order of speakers in this. And it really is a hit parade, actually. It really does indicate that Ozane has gone up in the hit parade, and for example, Ornstein has gone down in the hit parade, indicating that somewhere people were beginning to feel that maybe, despite the fact that Ornstein was more distinguished, Ozane was getting the right idea. Okay, here are some more dates that are, right, Mezevich observed that liquid crystal had more than one viscosity. It took a long time to publish because of the war. Interestingly, right, the introduction of the liquid crystal order parameter by Tsvetkov, who had been a student of Friedrichs and had taken over his group when Friedrichs had been carted off to the Gulag, right? And interestingly, the paper was written in Leningrad, and it was written nevertheless in German, right? In 1949, the statistical properties theory of lyotropic liquid crystals by Onsager, the Frank elastic theory, 1958, the Meyer-Sauper theory in the late 50s, the smectic C phase, well, the textures from the late 50s and its identification already in Kent by Alfred Sauper and co-workers in 1967. I just wanted to show you some pictures of the Grandjean theory, which is on the left, and the Meyer-Sauper theory on the right. There's no suggestion, incidentally, that Meyer and Sauper had ever seen the Grandjean theory, but nevertheless, you can see that it's the same thing. At least at the bottom, it's the same thing. So the interesting thing is, given that there was such a good theory at the time, why was it not accepted? And that's an interesting sort of intellectual story in itself. It was the wrong time. It was the wrong intellectual climate, because the idea of an order parameter hadn't yet been developed, and he was using cos 2 theta, which is equivalent to a half 3 cos squared theta minus 1, which is what, of course, we use nowadays. But going from something to something else doesn't have the same impact as going from zero to something. You know, that the ordered state has a non-zero something. There was a rivalry between the French and the German workers. Friedel thought at the time was too early for theory. Ozane read the paper, but actually it turns out just misunderstood it and thought that it was another version of the Born theory. And Grandjean was probably, he didn't have that kind of, you know, that kind of spirit somehow. He was too nice a guy. Actually, he changed fields entirely and he became an expert in mites. Mites are very small kinds of spiders, so he became a giant in the mite world. But what is interesting is that his view, in a certain sense, was more modern in outlook, because he didn't ask what is it that is causing the molecular field, right? Just like Weiss and Curie didn't. He just said it's there. Somebody else can worry about why it is there. Whereas Meyer and Sauper were thinking, well, maybe it's the dispersion force. You've got a you've got an anisotropic dispersion force. And they were right, but it isn't what causes the liquid crystal phase. Okay, I want to draw your attention to the Onsager work, right? Not because nowadays this is standard and people can do this, but at the time the key point was that Onsager said you've got effectively hard spherocylinders, but that he had to derive the fact that you've got hard spherocylinders. He had to say you've got salt and water and you've got double layers and so on, and these things are giving rise to effective excluded volumes. So it wasn't just a question of saying, gosh, there's excluded volumes, of course we can do this problem, right? There were a whole set of things that he had to do in order to get them, each of which, you know, are hidden now when somebody takes it out and says, please, can I do a simulation and turn the handle with an excluded volume. Not that that in itself can be quite interesting, especially when you've got colloidal systems that fit together. Right, Charles Frank, of course, is the authentic English hero. So, although actually he was born in South Africa, and so here are the Frank elastic constants. Actually, what I wanted to show you, this was his paper because he was a postdoc with Debye, and I just wanted to show you because this is one of the few examples of seeing a paper by somebody English written in German. Von F.C. Frank, Oxford. Okay, so, here's the 1958 paper. One of the principal purposes of the paper is to urge a revival of experimental interest in this subject. And you will see that he says that, that basically he's recapitulating Ozane's theory. He does a little bit of fiddling. He puts some constants equal to 0 and so on. But still, basically, and I don't think Charles would have said that this was a super original contribution, but it was necessary at the time, and it's also an interesting paper because for the first 6 years it was not cited at all. It was not until 1964 that this paper was ever cited, and yet everybody who writes an article, not absolutely everybody, but most people who write papers on liquid crystals like at least to pretend that they have read this paper. But for 6 years. So, and of course, had Frank been subject to the kind of pressures that we are under now with impact factors, they would have said, well, Frank, I think your job. We'll just have to see whether your paper gets any citations next year, won't we? Luckily, Morris Price was made of stronger stuff. Okay. So the development of hydrodynamic theory is in the early 60s. The first International Liquid Crystal Conference was in 1965, and the statistical mechanical theory, which almost everybody used by Deugen, dates from 1970, and there was, of course, nobody called Landau-Deugen. It was not the same, right? I wanted to draw your attention to this statement by Ericsson, right? in studies of the static behavior of liquid crystals, it is common to ignore or to treat in an obscure way the stress tensor and other representations of force. And it's certainly true that Frank, when he was writing down these things, what he said was, I'm going to write the free energy, right? I'm not going to worry about exactly how the forces work. So Ericsson, and of course this school at was a great school of rational mechanics at Johns Hopkins. Our treatment emphasizes this. The theory seems interesting. It is one of the few mechanical theories which involve an asymmetric stress tensor. So he's talking about how, if you like, the restoring force can put on body forces which can actually turn the fluid as well as simply turning the director. Because if you had just been thinking about free energy, you wouldn't necessarily have thought. I mean, nowadays, now that we are used to the idea that there's a whole class of hydrodynamic theories, and it's a question of whether the order parameter is conserved or various things like that, that's not such a hard thing. But at that time, it was quite revolutionary. Asymmetry is associated with the presence of what they call body couples and couple stresses, right? And in principle, one can calculate these for some physically realizable situations. Okay. So just to make some points about this theory, it requires a stress tensor, and the theory must also be compatible with the Frank-Ozane free energy minimization, right? And there were attempts. Ozane had a student called Anzeles who had tried to do this, and actually when Leslie, the theory was actually produced when Leslie went to visit Ericsson, and the first thing that Ozane did was, that Ericsson did was to give him a copy of Anzeles' thesis, apparently. And so Frank, who knew no German, this is Frank Leslie, knew no German, was sitting there with the German dictionary and Anzeles' thesis and so on. Okay. So the modern theory generalizes and corrects Anzeles. The main problem is it's really hard, or at least it was at that stage, getting the covariant derivatives right. He found 6 independent viscosities. At a later stage, one of these was reduced to 5. Okay, but right. Okay, so yes, of course, this theory is absolutely key in getting the device industry going, because you did have to be, otherwise everything would have depended just on tinkering. And of course, tinkering is great to get going in some kind of technology, but it doesn't help you to design something before you start. Here's a picture of Ericsson and Leslie taken in Scotland. Perhaps just before, I wanted to say that, of course, the other thing is it wasn't only right from the point of view of being self-consistent, it was also empirically right. And the fact that it was empirically right had to be established. And that is not as simple as you might think. So, right, just want to emphasize that that's the case. Okay, here's a picture of the great Landau. And of course, all Landau theories are based on a paper written in 1930, actually a couple of papers written in 1937 that appear, if anybody is interested in Landau's collected works, and which I would recommend as being well worth reading. De Gennes was the first person who took this theory and made it work in the context of liquid crystals and identified the order parameter, that's this thing here, that is a tensor order parameter, but is related to the director and also to the scalar order parameter that Svetkov had been using. Now, I'm taking some slight liberties here with history, because this is how we usually identify these things nowadays. But of course, De Gennes said the point about an order parameter is that it's an order parameter. You don't actually have to identify it with something microscopic, although, of course, we are much tempted to do so, and at least some speakers, I think, are going to talk about the way in which we would do so. And of course, it was not only this theory that enabled de Gennes to get the Nobel Prize, but certainly was one of them. Right, so I just want to make a few points. I'm sure that these points will be recapitulated later on. Landau theory was originally a static theory. You wrote down a free energy, right, and it was valid close to a phase transition because it involved the expansion, the Taylor expansion, indeed, of a free energy in terms of an order parameter. And it uses the symmetry to decide what kind of terms are allowed, and as a result, whether or not the phase transition is first or second order. Well, it now turns out, of course, that it's inconsistent if pushed too far. The idea of a second order phase transition, well, it might be something that you do as an undergraduate, but we all know that we can still talk about first order phase transitions, but otherwise we need to talk about continuous phase transitions that you need to be slightly more careful. Right? You can give it a dynamic component, and certainly in the context of superconductivity, you can give it TDGL, the time-dependent Ginzburg-Landau theory, so you can give it a time-dependent contract. Right? To have a chance of working, any dynamical theory must be consistent with what the fluid is doing, if you like. And the TGDL is a wrong first approximation to what's going on in liquid crystals, but of course people do try it to get some kind of idea, sometimes particularly if you mess around with the relevant viscosity. Okay, right. If you're a mathematician, usually you take the dynamical variables, the variables that enter the hydrodynamic theory in some sense as given. But a theoretical physicist might reasonably say, how do I know which ones to use? And he'll be asking about which kind of modes occur, what kind of symmetries are broken, and so on. So it's the most slowly, right? So the idea here with the Q-tensor theory, which I'm sure people must be talking about here, is that we have generalized the Landau theory, right, in such a way that it's consistent with the Landau theory, consistent with the hydrodynamics, but somehow in the process of so doing, we've now gone a long way from the phase transition, and we're now so there are at least some questions that if you're talking about this kind of thing, there are at least some questions that you have to ask along this road, it seems to me, to say, yeah, I'm doing something that's allowed, and so on. So I don't want to discuss any more other than to say that those are active areas of research. Okay. The one thing I haven't talked about is topological theory of defects, and I want to mention that because when we wrote our book, Jacques Friedel wrote me a very long letter. It must have been 7 or 8 pages, and it began, "Dear Sluckin," and you knew it was going to be not very good, and it was to the effect that that I was not taking into account the most important thing about liquid crystals, which was the optical signature through the textures. And if you didn't take account of the optical signature of the textures, you'd somehow missed something important in the liquid crystal story, right? And so the textures are signatures of the defects, right? You can't see the molecules being aligned. You can't see the layers, right? You've got to do so indirectly. Occasionally you can do so through the Grandjean textures or something like that. But the order parameter structure, the textures follow from the order parameter structure, but they aren't the same thing. And so the idea somehow is that can you invent a technology that will take you automatically one way, like the people who did crystallography were able to solve the phase problem and turn the process of turning a crystallographic picture into a molecular structure from being a work of genius to being a work of genius of the mathematician who produced the algorithm. So I will leave this question to others, but just to say that I have omitted it, and I think probably. Okay, conclusion. There is no conclusion. If there were a conclusion, we would not be here. right? I just want to have some thoughts. They're not really thoughts, they're pictures on liquid crystals in science. Here is mathematics at the center. We have in this house some chemists, some physicists, a number of people who are expert simulators. I don't know whether we have any engineers. In other meetings I go to, there are biologists, and occasionally we have people who say, ooh, isn't that cute? Not something that I would expect anybody from here to say. Of course, even at home. All right, a whole variety of different methods of applied mathematics which will be relevant and for which individual people who are doing these things will be experts on, but not always experts at the same time. Dr. Gartland being the exception, of course. And, okay, so I just want to acknowledge my co-workers, David Dunmer and Horst Stegemeyer, my teacher, Geoffrey Luckhurst, Taylor and Francis and Oxford University Press, who published my book, Peter Knoll and Anatoly Sonin, who wrote key stuff in German and Russian, sent me some stuff, older colleagues and informants who wrote me stuff to tell me how they saw things, some unfortunately departed colleagues who told me things but have now died, some others whom I would have liked to talk to but died before I get a chance to talk to them. Everybody who helped me understand the labyrinthine German of Otto Lehmann, those 100-word sentences, are not something that I could manage by myself. And the university, who had patience, even though this work is not funded, but I have to tell you they've lost patience. So, here is the commercial break. Here is the book for your university's library, right? It has all of the papers in it and the stuff, right, and which you should, right, which for your graduate students to copy, of course, that's actually what happens, and certainly for people in Wikipedia, apparently, to copy, but only in English, I should say, I haven't, right? And this is the version for your spouse, and for those mathematicians who are here, who have not heard this story before and want a more leisured attempt at it. And if you buy the book, it will go to my services rendered fund, and I may be able to afford to come to the next meeting. And thank you very much for having me.
Very much, Tim. It was really a delightful talk. I think given the time, I think we'll break now for coffee. And we'll have a chance to discuss and ask Tim questions, and we'll reconvene here in a half an hour at 11:30.